Hi, welcome to Distinti's review on quantum computing. This is an impromptu video. This is now going to be the T12 video. The T12 video was going to be showing the final death throw of quantum mechanics, but in doing the research for that video, I stumbled across this. So that video is now going to be moved to T13. This is now T12. Okay, in doing the workup for the video to show that quantum mechanics is completely unnecessary, it will never be part of a theory of everything, I stumbled across a lot of flagrant errors in quantum computing, which was going to be part of that one, but it became a whole video on its own. And I'm going to put the links for these videos in the top line, so people, or the low bar, whatever they call it, so people can get to them. And the first video, at 6 minutes in, they claim that because they're using quantumly entangled qubits, that they're going to be able to do error correction on the qubits. Okay, excuse me. Well, first of all, in the T11 video, I show that quantum entanglement is complete nonsense. I can show all of the things that they expect with a quantum entangled Bell experiment is just a simple byproduct of normal physics. There's no entanglement there. They're completely delusional. And second of all, when you have two bits, okay, even if they're entangled, it doesn't matter. Because if one bit is wrong, you can only detect that there's an error. You cannot correct. You cannot determine what the true value was. If you look up Hamming error correction, in order to correct a single bit, you need 3 bits in total. So I'm sorry, that will not work. And then there's the next video I went into, and it's complete puffery. I mean, all the things they think quantum computing is going to give them, and it's completely just over the top, walks on water, blah, 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 blah. I'm going to show you that quantum computing is really in a state of disarray. It's really ridiculous. And this video here is one that basically gives away all of the silliness. In this video, the Dr. Dario Gill from IBM Research, and he's actually doing something for MIT Venture Capital and Innovation. Okay, so what happens? At 12 minutes and 23 seconds, now this video was posted in 2017, 2 years ago. Okay, so what does he say? We believe that small practical quantum computers are going to be possible, means they're not possible now, and we are building them now. It requires reinventing the whole stack. So evidently they haven't already reinvented it, because otherwise that would not be a requirement. So at this video posted in June 2017, they're saying they don't have one yet. Okay. In the next few seconds, at 14 minutes and 21 seconds, they make the claim you will not ever be able to have a quantum computer. However, you will be able to access one via the cloud in the future. And the reason why they're saying that you will never have one on your desktop is because they require incredibly expensive cryogenic cooling down to 15 millikelvin or some ungodly low temperature. Fine, no problem. But what they're still saying is that you'll be able to have access to one in the future, which means they don't have one. And the next statement, because we believe that, we have created a small quantum computer and made it available to the world. Wait. Whoa, hold on a minute. They just got through saying they didn't have one, and now they say they have one. Okay, let's go back and review. Remember now, this video is in 2017, 2 years ago. Let's look at it again. We believe that a small practical quantum computer are going to be possible, and we are building them now. It requires reinventing the whole stack. 1421, you will not ever be able to have a quantum computer. However, you'll be able to access one via the cloud in the future. And because we believe that phrase just came after the previous one, we have created a small quantum computer and made it available to the world. So is this the past or the present? Okay, now, maybe I'm just arguing semantics here. So let's go on. At 1530, they say what's coming in the next few years, this is after that now, what's coming in the next few years are machines that no classical computer will be able to emulate. Well, wait a minute, does that mean now that existing computers can be completely emulated? I mean, Does that mean all present technology is emulation? Maybe what they put on the internet is all emulation. Now, the important part of this is going to be part of my argument for the T13 video, okay, where I'm going to argue that, hey, if quantum mechanics, if quantum computing could be completely emulated by a deterministic computer, perhaps all of the underlying physics is deterministic, and we're only applying this quantum voodoo because probability is what we use when we don't have all the information to do it deterministically. But that's getting off the subject of this video. Okay, but the video that they put online, they call it the IBM Quantum Experience. They don't call it the IBM Quantum Access to a Quantum Computer. They call it Quantum Experience. This sounds like a Disney theme park simulation ride. You know, like the Star Wars experience or the undersea dinosaur experience. It sounds like a simulation. And if emulation is better than present technology, that's what they're saying. Okay, they're saying that classical computers can emulate existing technology if it did exist. So what's the point? Okay, so they're probably better off to put simulation online. Okay, then 7 seconds later, and they says, because at that time, in other words, in the few years when they say classical machines will not be able to emulate, you're going to have an order of 50 qubits, which means we don't have 50 qubits now. Back in 2017, what they're saying. Think about that. That's 2 to the 50 states. Now, well, hold on a minute. Hold on a minute. 2 to the 50 states. I thought quantum qubits were supposed to be able to have a complete continuum of states. What they're saying now that a qubit can only have 2 states. And that's 2 to the 50. This is like binary numbers. What's going on here? I mean, my computer right now is a 64-bit machine. That's 2 to the 64 states. What's going on? So what we're saying then is in 2017, a standard computer, okay, can emulate these quantum computers and presently do a better job. Because evidently, we're going to have to get to much higher than 50 qubits, but the qubits can only have 2 states each, which doesn't agree with what they're telling us is that a qubit can have all states simultaneously of a quantum molecule, not just 2 states. If it's 2 states, why bother? You could just use binary. Why do you need a quantum bit if it only has 2 states? And this doesn't add up. It's just too much things that just don't make any sense, too many contradictions, and it's not done yet. Okay, so I figured, well, maybe this guy is just, talking out the side of his face. Maybe he's just, had a bad day, and maybe he's just misrepresenting stuff, or he's just tongue-tied. I get that way too. When I have my videos, sometimes I get words backwards. I do that too. So let's give the guy the benefit of the doubt. And let's actually go to the IBM quantum thing that he described in his video. Now, this is the state of the site in 2019, 2 years later. Okay, and what they say here is IBM Q is the world's most advanced quantum computing initiative. Wait a minute, they didn't say the most advanced quantum computer. It says quantum computing initiative. That's not a computer. That's an initiative to build a computer focused on propelling the science and pioneering commercial applications for the quantum advantage. Well, if you're pioneering, it means you haven't settled yet. You have no settlers. That means you have no applications. And this is 2 years later. They're still pioneering. All right, let's keep on going. So at the heart of IBM Q system is the Transmon qubit. Successive generations of IBM Q processors have demonstrated the potential of supercomputing Transmon qubits as the basis for electrically controlled solid-state quantum computers. Okay, the potential. We've only demonstrated the potential. We haven't realized one. That's what this means. They don't have one yet. Okay, they still don't have one is what this is saying to me. And then, I'm sorry, on the previous page, they give a little link to look at the existing hardware. Okay, so I clicked on that link. It brought me to this page. And this says these are the existing Q systems that are available. There's one in Tokyo and one in Melbourne. Okay, if you look at down the little paragraph on the bottom. I don't know if you can see it in the video. Quantum computers are rapidly emerging. Pursued for decades in research labs, prototype machines are today getting bigger and more capable. Well, quantum computing is still in its infancy. This is like how many generations later? I mean, we've been talking about quantum computing for how many years? And just 2 years ago, they say we have a couple of qubits and we're still in its infancy. I mean, this is a lot of years for computers. And significant progress is being made across the entire quantum computing technology stack. Today, okay, here's where we get, IBM has several real quantum devices and simulators available for use on the cloud. Okay, so they say they have several. Doesn't mean a lot, just a few. Okay, so I'm trying to find a link to explain what these devices are. Let's see, I forgot what the next page is. So here's IBM Tokyo. It is allegedly the highest one that they have. And you will know that over here, they put the properties and they say it's got 20 qubits. They don't give a last calibration date. They don't give a frequency. They don't give a time, T1, a T2. They don't give a gate error rate, and they don't give a readout error rate. Well, that looks like a simulation to me. Simulations don't have to be calibrated. Simulations, you can set whatever error rates and whatever else you want because it's a simulation. And if you go look at all of the other devices that are out there, they all are missing the same information. All they give you is the number of qubits. And all the other qubits, 20 seems to be the most complicated machine they have. So that other guy was talking about when we get to 50 qubits. Well, right now it doesn't look like they've gotten farther than 20. Okay, and it doesn't look like that's a real one. It looks like it's a simulation because of all the missing information. None of these look like they're real because all of the error rates, which would be part of a real system, aren't posted. So how are you supposed to use it? Now, maybe this page is just not kept up to date. I would think if this is their flagship technology, this thing should be overflowing with information to inform people like me as to all of these things. Instead, this entire site looks like a complete sham. It looks like a testimonial site. But now we go on and into this 2019, and I got all this little bullet information off to the side on another page. Today, more experiments are run on the IBM Q Experience hardware than its 32-bit qubit simulator. Well, that's interesting because the largest real one is only 20 qubits. And they have a 32-bit qubit simulator. I'm sure they've had that for the past 2 years now. It's a testament to the value of both. So only now are they having more people run on the real hardware than a 32-bit simulated hardware. Now, I'll bet you the 32-bit simulated is when people download the development environments, it's actually simulated locally on the PC. Okay, but now it keeps going on and it gets better. Okay, and what only IBM offers, we still have a lot to learn about how quantum computers work. Wait a minute, are we not developing the quantum computers? I mean, when you say it like this, it sounds like we're reverse engineering alien technology. And shouldn't quantum mechanics be telling us how they work? Aren't we developing this? Aren't we designing this? I mean, aren't you already fielding ones that work? I mean, this is just like, what are we doing here? This is like ridiculous. Who wrote this crap? And down here, the thing that they're using is what's called the Josephson Gate. Where's my mouse? Down here. And this is pretty interesting. I went online and I looked up what a Josephson Junction is. A Josephson Junction is nothing more than a superconducting means to store a quantity of current. Just like a capacitor stores a charge, or a magnetic tape stores a voice recorded in a magnetic field of the tape, or a magnetic core memory stores information in the form of a static magnetic field. So basically, it's nothing more than an analog memory. And because of that, it can only store a single state. Okay, you cannot store multiple superposition states in a Josephson junction. And they admit this. Let's look at the next page. And this on the bottom here is a blow up of this paragraph here. And it says there are a few different ways to create a qubit. One method uses superconductivity to create and maintain a quantum state. Well, a quantum state, not a quantum state superposition. And it gets better. Down here it says any heat in the system can introduce error. And I think that's their problem. Okay, because if it's an analog system, which something that can store a current is basically an analog value, an analog quantity. And because of that, it's susceptible to noise. Just like the old tape recorder cannot accurately reproduce the recorded sound because of the noise, the hiss that you get when you record on magnetic tape. And likewise, this system has to be susceptible to thermally induced noise. And therefore, the more qubits you have, the more heat is generated in the system, and the worse the system will perform. And they're working on that. They got noise amplification squeezes more computational accuracy from today's quantum processors, controlling nuclear noise and semiconductor qubits. So they're working on it. They're working on it. That's their problem, is the noise their own system generates. Because it's not really a digital system, it's a analog memory. And so this is a complete fraud. Okay, according to their own language, their qubits can only store a single state. It's not a quantum superposition of states. Therefore, it's complete bullshit to call this a quantum system. It's really just an analog memory. And that's where we come to the weirdest part. The worst part of this whole nonsense is the qubits are just to store information. They don't compute information. So what comprises a quantum arithmetic logic unit? This is not discussed anywhere on the website. I did a lookup for quantum ALUs, and there are references online. It requires me to look into it more. But from the couple that I looked at, it looks like they're done with regular standard hardware. It's just they got a thing called a two-way or bidirectional. I got to figure out what that means. But going back to what I'm saying, these qubits are not quantum. This thing looks just like a regular standard computer. So, I mean, I get what's going on. Okay, the money bags or the money people, the managers at IBM are offering all this free stuff in advance in order to obtain user familiarity. It doesn't matter if it's simulated at first. Get everybody used to using all the tools, so that when and if these devices become real, they'll have their foothold in a larger share of the market. This is what NVIDIA and Arduino did. By offering their development environment for free, they added value to the hardware that they sold. And because everyone jumped on their stuff because it was free, it became more difficult for other competitors to dislodge the users who are already familiar with using those tools. Okay, and this goes back to the old first to market paradigm. But when will this magic quantum hardware become available? My guess is the noise problem that permeates the online literature and mentioned in the video. The original video we looked at, we mentioned that there's a problem with noise. It gets bigger with the more bits you have. I didn't write down the time in the video that occurred, but it's in that video. So I believe this will ensure that the real hardware will never overtake the classical computer simulation, and this technology is dead on arrival. Forget the fact that it has no real advantage over classical means at this time. And the irony of this whole thing is that noise is a quantum mechanics construct. We engineers use noise modeling developed from early quantum mechanics. Okay, these noise models, these thermal noise models, were based on the assumption that the underlying system was deterministic, and therefore they were able to apply probability theory to give us a noise model which works pretty damn good. But here's the irony of this. That means quantum mechanics is defeating quantum computers. Okay, but sorry folks, I believe this technology, at least the IBM version of it, I haven't looked at the other methods out there, but I believe if I get into them, they're going to be equally as harky. So if they do get something to work, it'll be something completely different than what they are selling you now. And the reason why is, um, oh, well, I'll explain more. My final comment, there are many claims about quantum computing which will go unrealized. Okay, there's a lot of pie in the sky claims, walks on water, chews bubble gum at the same time. But I have a conviction that if you get enough engineers to pull all in the same direction, you will get something marvelous. However, the final product may be nothing like what was originally envisioned. And the example I have is the internet. Okay, if the government knew how much the internet was going to be a pain in its side, they probably would have banned it on the first day. Nobody knew what the internet was going to become. At the beginning, I thought it was just this annoying little, oh, we're going to do chit chat and bulletin boards and stuff like that. No idea how it was going to make my life better. Okay, nobody envisioned where it was going to go. Maybe a few did, and those are the people that probably made a fortune. Okay, but it's very likely that the next generation of computers will come from this effort. However, okay, just by pure fiat of the engineers, but in order to have advantage over existing technology, this new technology is going to have to operate not in the RF wavelength, the microwave wavelength, which they're talking about now for qubits. It's going to have to be in the optical wavelengths. And it'll have nothing to do with quantum superposition or quantum entanglement. It'll be some kind of nanotechnology optical computing using either blue-ray or ultraviolet wavelengths. Just like the present HD optical displayers today. It'll be kind of like the descendant of those guys. Okay, so that's what I am seeing is going to be the next generation. It's got to be higher frequency than microwave because our computers right now, our digital computers are operating with frequencies right now that are in the microwave region. So having quantum computers that operate in the microwave region is really not going to be a benefit. I don't see it. So it's going to have to be optical. And that means it's going to have to be nanotechnology or something to that effect. That's the only way to get advantage over what we have now. Because now we can make stuff where we can put a whole bunch in parallel and we can bypass the frequency limit of existing technology by putting hundreds and thousands of them in parallel and doing parallel computing. Matter of fact, most of the problems that they explain that are good for quantum computers are the same problems we apply using parallel computers to. So I really just don't see what the big deal is with quantum computing. I don't see any of the things that they've said that they are. They are not what they say they are. And there's just too much contradiction and too much nonsense going on. So anyway, let's leave it at that.